All right, hello, testing. Hello, testing the mic. Okay. Alright, good. Alright, let's get started. Hello, I'm Steve again. I did the chapter 3 from Monday, and I'll continue for chapter 4. So let's get right into it. So in this chapter, the whole point of it is really try to quantify the amount of information that's in a source based on the probabilities of the source symbols. And the way we think about information as like a numerical number, I'll give you an example. So let's say we have the source with two symbols, A and B, and their probabilities are 0.9 and 0.1. And let's say we receive the symbol A. Now 0.9 is a pretty high probability, and it's like much higher than getting a B. So if we having received the A, we didn't really receive much information because it's kind of already expected to get A most of the time. However, if we receive B instead, then that's like really more surprising. So what that means is that we received a lot more information because we weren't really expecting to receive a B. So yeah, information, the way we quantify information, one way to think about it is kind of how surprising it is to receive receive a certain symbol. And here's the definition. So if there's an event of probability P, then the information given by this event happening is just just k log p for some fixed k less than 0, and that's just chosen based on the context. And the way we choose the k here, for radix 2, we pick k equals -1 on ln2, and the information is measured in bits here. And in any arbitrary radix r, we pick k equals -1 on ln r, and the information is measured in radix r units. It turns out that this definition of information, it works really well because it has all the properties that we want here. It's like, as the probability kind of increases, this should decrease because the constant is negative up here. For smaller probabilities, the information goes up. And another nice thing about this is that we can kind of, if we have two independent events, we can kind of we can add up the information of each of the probabilities of the events. And yeah, so we can also define a measure of the overall information that's inherent to a source based on this new information quantifying function. So here's what we call the Shannon entropy. If we have a source S and it has symbol probabilities Pi, that should be P1, P1 to PQ, the Shannon entropy for S for radix R is kind of like the weighted sum of the information. So probability times the information gained by that probability. So it's kind of like the expected information of receiving a symbol. So yeah, and if r equals 2, we can actually just omit the subscript on h. That's just convention. It saves you a bit of writing, I guess. So here's a question. Find the average length of the binary Huffman code on the source S with symbol probabilities 0.6, 0.2, 0.1, and 0.1. Compare this to the entropy of S. So I'm not actually going to show you how to get the Huffman code because you can refer back to either the lectures or the Monday session. But yeah, I'm just going to tell you that if you do run Huffman's algorithm on S, you're going to have an average length of 1.6 here. And if we calculate the entropy, the radix 2 entropy, we get this sum over here. So this 0.6 log 2 0.6, that just comes from the first symbol probability, minus 0.2 log 2 0.2, and so on for each of the probabilities. And if you calculate that using your calculator, you get 1.5709 ... And if you notice, it's slightly smaller than the average length of the Huffman code that we found, right? And it kind of makes sense. This entropy calculation, it's kind of saying on average, the source symbols entail about 1.57 bits of information. So, if we're going to make any code based on this source, we're going to need at least that many bits per symbol. So that's why the Huffman code, the average length is slightly bigger. And the reason why the Huffman code average length is like only slightly bigger than the entropy, it's sort of explained by the fact that the Huffman code is a minimal code. This is not like, it's kind of an iffy explanation because sometimes Huffman code can be pretty bad. But yeah. So it turns out that the entropy of a source, like the average information in a source, that has an upper bound based on the number of symbols in that source only. So if we have a source with q symbols, the maximum entropy theorem says that the radix r of Shannon entropy of S is going to be less than or equal to the number, like the log of r of the number of symbols. And the equality holds if and only if the symbols are all equally likely. So if you want to prove this, you need some inequality called the Gibbs inequality, and here it is. If you have P1 to Pn and Q1 to Qn as probability distributions, as in think about these as like the probabilities of symbols in two different sources, each with n symbols, then you get this inequality here. The left side is really just the radix r Shannon entropy for the source with source symbol probabilities P1 to Pn. And the second one here, it's not exactly the entropy, but it's kind of like as if we mixed up the probabilities of these distributions. Like we use the p's to kind of do the weighted sum, but the informations, like this kind of like I of qi, these ones are from the q probabilities. And we also have equality if only if pi equals qi for all I, so if these distributions are exactly the same. And yeah, Gibbs inequality, it's really just a fancy way of saying that if you mix up the probabilities in each term in the entropy calculation, then the result is as big, like at least as big as the actual entropy. I don't see this inequality that often in the course, so probably don't need to know that much about it. But famous last words, maybe. But yeah. Okay, so more interestingly, there's actually a mathematical explanation of the reasoning that we had before behind the average code length being at least the entropy. And this is called Shannon's first source coding theorem. If you have a source with q symbols, probabilities P1 to PQ, and if you have C as any radix R uniquely decodable code for S with code word lengths L1 to LQ and average length LR, you actually get that the entropy is less than or equal to the average length of the code. And the equality holds if and only if the probabilities are exactly equal to the radix to the power of minus the length corresponding to the code word for that probability, and the Kraft-Macmillan coefficient is exactly equal to 1. Now, I don't know if you remember from the Monday's seminar, but this equality here, the Kraft-Macmillan coefficient it being exactly 1, that's really saying the code words are designed to like maximally use up the like some sort of decision tree that represents the code words. And yeah, if you want to prove this, you need Gibbs inequality and the Kraft-Macmillan inequality, and that's like Kraft-Macmillan theorem. That's in the lectures. I'm not going to go through the proof. So we can actually draw ideas from entropy in order to come up with some pretty good I codes. And one of them is called Shannon-Varno coding, which assigns code word lengths based on the source symbol probabilities and before like actually constructing the actual code words. And the way it works is, well, if you have a source with q symbols, probabilities P1 to PQ, we first set all the code word lengths to the ceiling function of minus log pi. And this r, it's just for a radix. So if we want a radix 2 Shannon-Varno code, then just sub in I equals 2. So yeah, we just set all the lengths first based on the probabilities. And then the Shannon-Fowler code is just the standard radix R I code for the lengths L1 to LQ. And yeah, I went through what a standard radix R standard I code was in the Monday seminar, so you can have a look at that. But let's go through an example. So, okay, let me get on my iPad. So we had a source with 4 symbols, S1, S2, S3, S4. Probabilities were 0.5, 0.25, 0.125, 0.125. And we want to construct a radix 2 Shannon-Fowler code. Okay, so the first thing we do, we figure out the lengths of like the code words that we should have. So for the first code word, the length should be, because we're in radix 2, we take the ceiling function of minus log 2 for the radix of the probability. So the first one here. And, you know, surprise, surprise, this becomes a very nice calculation. Log 2 of 0.5 is actually minus 1. So we get 1 for this. For the second one, the length, we just do a similar calculation. Minus log 2, 0.25. That's going to be 2. And L3 and L4, they have the same probability, so they're going to have the same lengths. So minus log 2, 0.125. And, you know, surprise, that's also a very nice number. That's going to be 3, even without the ceiling function. And yeah, similarly, L4 is going to be 3 as well. Same probability. So now that we have the lengths, we just construct the standard I code for this of radix 2. And on Monday, I showed you the lexicographically smaller stack kind of idea for building the standard I code. I'll just show you the tree version. So the first code word, you just branch out. You do a 0 and just like stop. Just call this C1. For the second code word, we need length 2. We can't branch out of this 0 here. We don't want C1 to be a prefix of anything. So we have to go down to 1. And we want a length 2, so we just branch out to the smallest one. So C2. Next, we want a length 3 code word. So we go down. It's going to be 1, and we got to go further again because we want length 3. And finally, length 4. Length 3 for the fourth code word. So the code words are C1 is 0, C2 is 10, C3 is 110, and C4 is 111. Okay. Should be pretty straightforward. And yeah, it seems more straightforward than Huffman's algorithm, if you remember. But the catch is that the Huffman's algorithm actually results in like the Shannon-Fowler code, it's like never better than the Huffman's algorithm. And yeah, despite this, like Shannon-Fowler coding is actually still pretty good, as I said before, because the you can prove this, but it turns out that the average coded length is always less than HRS plus 1, as in it's like the entropy plus 1. Remember, you can't do better than the entropy as the average length. So average length plus 1 as the upper bound, that's pretty good, in my opinion at least. Yeah, this is how you prove it. I won't go through exactly. It's just like exactly the same proof in the lectures. Okay, so yeah, in the previous section, we also dealt with extensions of codes. So what I mean by previous section, that was Monday. We dealt with extensions, and it was just encoding source symbols like 2 at a time or 3 at a time, etc. So I'll give you an example. If we had a source with 5 symbols and we wanted to find the entropy of the Huffman code for the third extension, that would be really, really hard and tedious. I would not do that because there are too many symbols. There are 125 symbols. Like, imagine calculating those like p log p values 125 times. So luckily for us, we have a very good theorem for that. it's very simple. The entropy of the nth extension is just n times the entropy of the original source. That's it. Just never expand expand these symbols for the extension. Just use this because it's so much faster. And turns out that this theorem, it really gives us an interesting result. You might have noticed this already. So remember in Monday's seminar, I showed you how using the second extension kind of reduced the average coda length compared to just using Huffman's algorithm on the original source. The thing is, if we took more higher extensions of the same source, it actually results in better and better compression. And Shannon's the previous theorem about source coding probably wasn't Shannon's, but okay, this is Shannon's source coding theorem. If you want to encode s to the n, so the nth extension, by a Shannon-Fano or Huffman code for increasing n, so higher and higher extensions, the average length actually goes down towards the entropy of the source. So it's saying as an average length per original symbol. So this thing here, it's the average length for the nth extension, radix r, divided by n. That's going to be the average length per original symbol. That's going to go to the radix r entropy as n goes to infinity. So for both of the Shannon, Fano, and Huffman codes. Okay, just pushing through. We're going to talk about the entropy for Markov sources now. So remember, the entropy of a source is just a way of measuring the average information per source symbol. And so, Markov sources is a source, so why don't we just apply this kind of idea to that, to measure the information in Markov sources? Well, it's just a matter of dealing with all the extra probabilities. So let S be a Markov source with Q symbols, transition matrix M, and equilibrium P. The conditional information of Si given Sj is just the the information's function of the conditional probability of getting Si after Sj. And the conditional entropy is sort of the the weighted sum of the of the jth column. Yeah. So this thing here is you just look at the jth column probabilities of the transition matrix, and just find the entropy of that. And there's more definitions here. The Markov entropy, it's the weighted average of all the conditional entropies. So for each column here, there's this thing here is for one column, the entropy of one column. You can think of it as the average information you get given that Sj was the last symbol you saw. The Markov entropy is just the weighted sum of all of those column entropies based on the equilibrium probability of that column. So first column, we find the entropy, we multiply by the equilibrium probability of the first symbol, and just continue that, sum it up for the other columns. The equilibrium entropy is just the entropy corresponding to the equilibrium probabilities in the vector P. Okay, that's quite a lot of definitions. To be honest, it is a bit of a trick calculating all these, but here's an example. So we have a source, Markov source. It has a transition matrix M and probably equilibrium P. And yeah, this thing, I did say this had to be the eigenvector of M corresponding to eigenvalue 1, but it might be incorrect here just because I couldn't be bothered making a correct example, but this example still works. So yeah, we want to find H of M of S, so the Markov entropy, as well as the equilibrium entropy in bits. So what does this mean? This is just radix 2. So to calculate this, remember this thing here, we needed the entropies of each of the columns. So we find the entropies of each of the columns, blue, green, red here, let's do that. It's a lot of calculations, just trust me on this. We get these three values here. The Markov entropy then is we take the values that we just found and multiply each of them by their corresponding equilibrium probability. So 0.53, 0.15, 0.32, they all come from this probability vector here. So like the blues, like I made it so that the blues match up greens and the reds. And you get 1.3 if you do this, apparently. The equilibrium entropy is just look at P, look at the probabilities in P, and just find the entropy based on those. You get 1.42. So if you notice, the Markov entropy is less than or equal to the equilibrium entropy. And it turns out that this is actually the case for every Markov source. So yeah, here's that theorem. And yeah, it's always less than or equal, the Markov entropy. And equality holds if and only if the source symbols are independent of each other. As in, like, the transition matrix is essentially useless. Doesn't really tell you anything about the probabilities based on previous symbols. And there is an intuitive way of thinking about this. A Markov source, if you remember, it's like it provides us more information about the source symbol probability. So like, in a sense, like it's more predictable than, like it's more predictable to like, actually let me say it again. It's like you're like less surprised by the symbols that you receive because of the extra information you have of the symbols. So like, as opposed to if you just had the equilibrium probabilities like on their own, like you're gonna have more information than that. So like, you know, the information in a Markov like source, it's gonna be less than or equal to the equilibrium. Yeah, it's like we know more about the source, therefore less surprising compared to if we know only the equilibrium probabilities. Okay, we can also take extensions of Markov sources and find their entropy. And here is a bunch of crap that you don't need to actually use. Never use this when you're trying to calculate the extensions, like entropy of extensions of Markov sources. Just ignore all this. We have a nice theorem for this, like before. We have that the Markov entropy for the nth extension is equal to n times the Markov entropy of the original source, just like before. It's like really the same. One slightly different thing here, the equilibrium entropy for the nth extension is the original equilibrium entropy plus n-1 times the Markov entropy for the original source. Just remember these two. Always use this when you're calculating entropies of extensions of Markov sources, because it's just so much better. Don't need to know very long formulas. And also, we actually have that the equilibrium entropy of the nth extension divided by n, it's actually equal to the Markov entropy when you take like larger and larger extensions. I've never seen this get used though, so just I guess just like put it on the back of your mind. Okay, so that's really it for that kind of like sources, like Markov sources and like the you know, the regular sources. Now we're going to kind of switch to finding or like quantifying the amount of information in like through a channel that has some noise. So if you remember, a noisy channel is just like it's as if like you have if you like send like some message to this channel, it might get corrupted like based on probabilities, like by symbol. And yeah, so we're gonna focus on this setting now. So yeah, in this setting, we need to have a set of symbols that's sent and a set of symbols that are received. And we call the set of symbols that you send the source. So like, we normally say that's A, and let's just say we have like U of them. And the set of received symbols is called the sink. We just usually call them B and like B1 to BV. And yeah, we're just gonna say these symbols, they have probabilities just like P of the symbol. So in addition to this, there's also a bunch of conditional probabilities, and which they kind of all sound something like the probability of receiving a 1 given that 0 was sent. So like, So in general, the probability of receiving a sync symbol, so like BI, given that AJ was sent, is just denoted like this. Very clear. So BI given AJ. BI received given that AJ is sent. And okay, here, following this, there's going to be a lot of definitions, and unfortunately you're going to have to know them. So, first one I'm going to cover, source entropy. It's just the entropy of the source symbol probabilities, easy enough. The output entropy is HB, which is just the same thing but for the sync symbol probabilities. And we also define conditional entropies. So this one here, it's like the entropy of the sync, so like the output symbols, based on receiving a single symbol, AJ. And that's just the conditional probabilities of each of the symbols in BI given the AJ, log of that as well. So like, it's like kind of like the similar weighted sum kind of thing. Similarly, we have it the other way around. We can have the entropy, conditional entropy of the source based on each of these sync symbols. And yeah, that's a similar sort of thing here. There's more definitions. The noise entropy, we denote by this. It's like the weighted sum of the conditional entropies, like B given the AJs for each of the AJs in the source. Each of them multiplied by the probabilities of the AJs themselves as well. Channel equivocation is like the other way around, just like switch the variables. And the joint entropy is sort of like the entropy of like the overall situation that we have with this like whole sync and source thing. It's like for every single pair of events that you can have. So like, we can, if there were like 3 source symbols and 3 sync symbols, you can like for the first source symbol, you can either receive like the first, second, and third sync symbols, and you just like you kind of like have like 9 pairs of events that can happen. So you just like enumerate all of them. It's like consider every single pair of those like source symbols and sync symbols, and find the entropies of those. Yeah, so this double sum is just saying that. Yeah, so that was just a like whole bunch of formulas. There are sort of better ways of understanding this. The noise entropy, it can kind of be seen as like at the amount of average information in the output given the source, and vice versa for the channel equivocation. The joint entropy, as I said before, it's like the average information of the channel as a whole, like accounting for every single possible scenario you can have. And okay, so I don't know if this will kind of make sense, but to me it kind of makes sense that the joint entropy is just equal to the entropy of the source plus the noise entropy. So it's as if like the information in the entire channel is really just the information in the input, so this is that part, plus the information that we get about the output given that we have the input. And similarly, we can go the other way. So that thing here, it was just the first and the third part here. We can also go the other way, and it actually, these two are equal, doesn't really matter which way. We see that the entire information in the channel as a whole is equal to the information in the output plus the information that we get about the source given that we have the output. So if you look at this part of the proposition we have here, we can kind of take the conditional entropies on the, not the conditional entropies, the noise entropy and the channel equivocation on the other side. We get this equality here. So this common quantity, these two values, which are the same, it's usually called the, it's called IAB, the mutual information between A and B. It's kind of like the measure of an average information that's passed through the channel, not just the channel itself as a whole. And here's a nice diagram that explains, kind of summarizes all these equalities. We have the entire information in the channel, accounting for every possible scenario you can have. That's going to be equal to the information in the source plus the information about the sink that you can get from the source, or the other way around. And if you kind of break that up, you get these three parts here. You can divide the entire information of the channel into these three parts. Okay, here's a question. We have a binary channel. There's two symbols, A1 and A2 in the source, and two sink symbols in the output. The probabilities are 0.4 and 0.6 for the source symbols. We don't know the actual probabilities of the sink symbols yet, and we see that the conditional probabilities are these. So receiving a B1 given we sent an A1 is 0.8, and so on for those. We want to find the average amount of information that passes through the channel. So if you remember what I said, the information that passes through the channel, that's literally just IAB, and we just use that. We can either use this formula or the other one. We're just going to use this one because it seems to be easier. And so here's a little bit of an aside before we go straight into the question. If we have a binary channel, the entropy can actually be found using only one probability, like the probability of just one of like the symbols, or source symbol or one of the sink symbols. And that's because there's only two symbols. Like if we know the probability of one of them, the other one's just going to be 1 minus that. So we usually we can overload the definition of H, so like the entropy function. We can overload it by just if we give like a real number, like between 0 and 1, we just kind of treat that as like the entropy of a binary, like entropy of a source with two symbols with probability x for one of the symbols. So yeah, this is a definition. It's like, you know, like the information of the first symbol, the information of the second symbol. And back to the question, finding the sink symbol probability, the sink entropy, which is this part that we needed here. That's going to need the probabilities of receiving B1 and B2, and as well as like a standard entropy calculation based on those. So we just use Bayes formula. Well, no, not Bayes formula, is it? Just like, yeah, I don't think it's called Bayes formula, but yeah, something similar. We kind of you know, we can calculate these PB1s and PB2s based on all the conditional probabilities we had based on the source symbols, and we also had the source symbol probabilities, so we can just use those as well. So yeah, if you calculate this, the probability of receiving a B1 is going to be 0.5. For probability of receiving a B2, don't need to do this kind of calculation again. It's just going to be 1 minus receiving a B1, so 0.5. And so the sink symbol probability, can't speak. The output entropy is going to be the new function, like the overloaded function, h of 0.5, which is 1. And to find the second part that we needed for the mutual information, we need to find these two values first. Remember, this was like a weighted sum of these two based on the probabilities of PA1 and PA2. And we see that this thing here is going to be h of 0.8. It's really simple because in the question we only have two symbols, and we just need to care about like the probability of B1 given A1 and B2 given A1. So we just need the probability of one of those. And similar sort of thing for the second one. And so to find the noise entropy here, it's just going to be P of A1 times this thing here, and P of A2 times this thing here. And trust me, you get 0.818. So finally, we just like bring it all together. We just solve the values that we found. And if you do that, you get 0.182, around that. So yeah, this is really saying on average, the amount of information in bits that gets passed through the channel is 0.182 bits. And it seems pretty bad, right? Like we're trying to send 1 bit of information per symbol, and yet we're only getting 0.182 bits per symbol through the channel. It's pretty crap. So, you know, can we improve this? Well, we actually can. And consider this scenario where this channel that we have, the crossover probabilities, consider that like as fixed. So like we have some fixed channel that we have to work with. If we do have that scenario, we can kind of like manufacture a source so that the source symbol probabilities kind of synergize with the crossover probabilities of the channel. What I'm trying to say is that there's like a specific, like for each channel, there's like a specific configuration of the source symbol probabilities so that the information that passes through the channel is maximized. And that's called the channel capacity. It's called, it's just denoted by C or CAB, and that's just the maximum mutual information you can get. And this maximum is taken over all possible probabilities of the source symbols, as I said before. Again, just to reiterate, we have a fixed channel. We want to construct a source so that the probabilities of the source symbols synergize with this channel so that the mutual information, the information that passes through, is maximized. So here's a question, just to show you how to do these, how to find channel capacities. Yeah, so the question is, for the binary channel we had before, find the channel capacity. And yeah, so finding the capacity of a binary channel, it's like for a binary channel, it's like sort of easy. Like it's not easy, it's like just easier than sources with more than 2 symbols. And the reason for that is because if we have more than 2 symbols, we have a lot of we have too many source symbol probabilities that we have to maximize the mutual information over. And that requires a bit of multivariable calculus. We're not going to go through that in this course, so we're just going to deal with binary channels. So yeah, so say, to find the capacity of a binary channel, we just let P be the probability of like one of the symbols, like sending one of the symbols, say A1, and so that the probability of the other symbol being sent is 1 minus P. So we can just use basic calculus to maximize the mutual information. It's like that, just depending on P. Like P is like really the only the only parameter that we can work with, or that we only need to work with, which is easy. Only like just single variable calculus. And to do that, we have to find an expression for the mutual information in terms of P. And to do that, we just do like a similar sort of thing, like because IAB is HB minus HB given A. And to find this, we need to find P of B1. Oh, we only need P of B1, not P of B2, because P of B2 is just 1 minus that. So if we do that, this is the exact same calculation that we did for PB1 last time. And in terms of P, now this one's going to be P, not an actual number, and this one's going to be 1 minus P. And these values, like 0.8 and 0.3, they just came from the example before. So yeah, we get this, and if you simplify that, you get 0.3 plus 0.5 P. And just for, this is the way it usually goes. You don't have to kind of define new variables. But yeah, for convenience, I'm going to let x be equal to P B1, which is 0.3 plus 0.5 P. Then what that means is that the entropy of the output is going to be just entropy x. So next, as I said before, to calculate mutual information, you not only need h of b, you also need h of b given a. And we also need that in terms of p. And to do that, we do like the calculation again. These two are just like exactly the same from before. They don't actually depend on p. This one will depend on p though, because we introduced these two over here. So it's just a way to sum again of these two values based on the probability of the first symbol and the second symbol in the source. And we get this. We get something in terms of p, but I'm gonna convert that into something in terms of x, because we define x like this, and it gets a bit easier when we do the differentiation. Yeah, so we set x equals 0.3 plus 0.5 p, so p is gonna be x minus 0.3 divided by 0.5, exactly here. And you get 0.977 minus 0.319x. You might see a discrepancy here, like timesing by 2, but that's like this because I'm omitting like a lot more of the decimal symbols here. So yeah, these are not exact values, I just truncated them just to make it look nicer. And so IAB is going to be the HB, which is just HX, minus this thing here. So minus 0.977 plus 0.309x. Now that we have the mutual information based on, like, in terms of x, we want to maximize that. And you might be thinking, why are we maximizing in terms of x? Well, it's really the same as maximizing in terms of p. Once we find the value of x that maximizes the entropy, maximize the what you call it, the mutual information or the entropy here, then we can find p based on that. So we first want to differentiate h of x, just to make our lives easier. And what happens is, you just use the normal differentiation formula. It's just a product rule. So I just expanded h of x, the definition, over here. Just use product rule and like bunch of differentiation, and you eventually get log 2 of 1 minus x on x. So, okay, this is a typo. This should be mutual information. d dx of IAB should be log 2 1 minus x on x. So that's just the derivative of h of x, plus the derivative of like this side here that we just neglected for a bit. So we found the derivative of this, we find the derivative of that, that's just 0.319, and we just add them together. Yeah, so again, yeah, this should be IAB. And yeah, we just want to maximize this, so we just solve this for 0. And if you set this to 0, like set this right hand side to 0, you get log 2 1 minus x on x equals minus 0.319. So taking the power to 2 to the power of each side, you get 1 minus x on x equals 2 to the power of minus 0.319. And you just use you just take the x to the other side and like do a bunch of algebra, and you eventually get x around 0.555. So yeah, so the channel capacity is going to be the h of 0.555 minus 0.977 plus 0.309 plus 0. Times 0.555. So this thing, we're just subbing x equals 0.555 into the expression we had for the mutual information this here. And that gives us 0.191. That's like sort of better than the value we had before, so which is still, we just take it as a win. Okay, that's that example done. Yeah, so finally, I just want to go through this very small topic here. If we have a binary symmetric channel, so the crossover probabilities are the same. So probability of like flipping, because it's a binary channel, it's going to be 0 or 1. The probability of flipping, like the channel flipping a 0 to a 1 or flipping a 1 to a 0, it's going to be the same. So if we have that kind of symmetric binary channel, then the capacity is just given by 1 minus HP. P is just the crossover probability. So like the probability that a bit gets flipped. And yeah, that makes it pretty easy. Yeah, so if you have a binary symmetric channel, don't bother with like all the differentiation and like all the very long calculations we did in the previous example. It's just this. And yeah, that's it for chapter 4. And Jay will take over to do chapter 5.
Hello. Testing if my mic's working. Okay, I seem to be able to hear myself. Okay. Yep, I can see my own stream as well. That's good. Alright. Thank you, Steve, for taking on the previous topic 4. I'll now be moving on to topic 5, number theory and algebra. So let's get straight into it. The first thing to look at is stuff related to modulo, or I guess modular arithmetic. So the first thing is to look at the division algorithm. So let a and b be integers, with b being greater than 0. Then there will exist some integers q and r, with r being within zb, such that a equals to qb plus r. So essentially you're taking some number and you're taking some divisor, b. You're dividing a by b to receive a quotient and a remainder. Okay. And yeah, that's exactly what I said here. We said that q is the quotient and r is the remainder. In modular arithmetic language, this is equivalent to saying that a is congruent to r mod b. So this number here that we first chose is congruent to its remainder under modulo b. Okay. All right. When r equals to 0, then a is a multiple of b, or in other words, we can say b is a factor of a, or we can also denote it as b, and then this little pipeline operator b divides a. Okay. A greatest common divisor is defined as if d divides a and d divides b, then d is a common factor of a and b. All right, so that's just saying, for example, the number 12. 12 is divisible by 3. And similarly, 15 is divisible by 3. So a common divisor, common divisor of 12 and 15 is 3. Okay. Next, it is therefore the greatest common factor if d is the greatest among all common divisors. Okay. So in this case, 3, for example, is the greatest common divisor because there's no other common divisor between 12 and 5 that's bigger than 3. Right? On the other hand, if we look at, for example, let's say 15 and 150, right? We could have that 3 here as a common divisor as well. 3 is a common divisor. But 3 isn't the greatest common divisor, right? The greatest common divisor would be 15, because 15 divides 15. 150 is also divisible by 15, and there's no greater common divisor that is bigger than 15. Okay. Greatest common divisor. Okay. So how can we compute this greatest common divisor in a, I guess, systematic way? Well, one way to do that is to use the Euclidean algorithm. Okay, so the, I guess, process is to first divide a by our divisor b to get a remainder r1, and then we just note down that b is r0, and then between r0 and r1 we repeat the same process to get r2, and then we repeat the same process between r1 and r2, then r2 and r3, then r3 and r4, and blah blah blah, until we finally get a remainder that is 0. Okay, then the greatest common divisor will be the remainder just before that. Yeah. So this is okay. I'll do an example here. This should be something you should have learned from 1081. But for example, if I'm looking at the common greatest divisor between, let's say 17. Oh no, 17 is prime, so that's not a good example. Let's not do 17. Let's do, for example, 21 and 15. Okay, we know behind the scenes that this should be equal to 3. Right, should be equal to 3. Right, but let's use the Euclidean algorithm and see if we can get that answer. Right, so we take 21 and we look at how many multiples of 15 are in 21. Only 1, so we do 1 times 15. Okay, and then what's the remainder? Well, the remainder from 21 minus 15 would be 6. Okay, and it's also a good note to just highlight these numbers. Okay, just a trick that you should have learned from 1081. To, I guess, put focus on the numbers that you want to care about. Right, so we care about 21, we care about 15, we care about 6. Next, this is like our A, this is like our R0, and this is like our R1. So now let's proceed to the next step using our R0 and R1. So we have 15 equals to 2 times 6 plus 3. Okay? So this is like our R0, our R1, our R2. Now let's repeat the process with R1 and R2. So 6 equals to 2 times 3 plus 0. Okay? And we see that we terminated the process because we ended up at 0. And so the greatest common divisor would be the remainder just above 0, so this one here. Therefore 3, and that directly coincides with our own, I guess, knowledge already, right? The GCD of 2115 should be 3, and this algorithm also gives us 3. And in general, this will always work systematically. Okay? Chinese-Remainder theorem. What happens if we have multiple congruences? So the theorem states that let P and Q be co-prime integers. That is, the greatest common divisor of P and Q is equal to 1. And suppose that X is congruent to A mod P and X is congruent to B mod Q. Then there is a unique solution modulo PQ. Okay? We won't really be using this theorem much at all in this chapter. It might pop up a little bit in chapter 7. But besides that, it's just another fact about modulo that you can know about and use whenever. Okay. Invertibility. So for invertibility to make sense over the field Zm, so this would be the field of numbers, or like the set of numbers taking you from 0, 1, 2, 3, all the way to n minus 1. We have the following sufficient and necessary condition. An element A in this Zm is invertible, or otherwise called a unit, if and only if the greatest common divisor between A and the modulo we're taking M is equal to 1. Or in other words, A and M are co-prime. Okay? And then the set of units forms a group, and we denote this group by U subscript M. And it's equal to all of the A's in the bigger set, or the bigger field Zm, such that A and M are co-prime. Okay? Note that if M is prime, then UM will just be everything from 1 to M minus 1 excluding 0, right? Because the GCD between 0 and any other number is 0, so it doesn't satisfy this condition. So it's just everything from 0 to M minus 1 excluding 0 itself. Okay? And the number of units, okay, so the number of, I guess, the cardinality of UM, we denote by a function called the Euler Theorem function. I'll just call it phi m, right, phi of m. Okay. So an example would be if we're looking at, let's say, um, and this time we choose, let's say m is, I don't know, 12, okay? So we're looking at u12 right now, yeah? So what are the numbers in z of 12? Well, z of 12 are right here. Is the set 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? And so we're looking at all the numbers in here that are co-prime with 12 itself, right? So in this case, UM would consist of, well, not 0, right? Because 0, GCD with 12 would be 0. 1 would work. 2 wouldn't work because 2 has a common factor of 12. 3 wouldn't work because 3 has a common factor of 12. 4 wouldn't work because 4 has a common factor of 12. The next number that would work is 5. 6 wouldn't work. 7 would work. 8 wouldn't work. 9 wouldn't work. 10 wouldn't work. 11 would work. Right? So it's just these numbers within Z12 that are co-prime of 12 itself, and that's why they form the set U12. Okay? And in this case, phi of 12, right? You could see that this is exactly 4, because there's 4 elements in this set. Okay? Alright, so this function here is a function that returns the number of integers less than or equal to n that are co-prime with n. Okay? So exactly an example I showed here. We reveal a few facts about this function. This function is multiplicative. So if a and b are co-prime, then phi of AB just equals to 5A times phi of B. If P is if P is prime, then 5P is just P minus 1. Again, for the same reason here, right? Within this set, if this number M is prime itself, then everything will obviously be co-prime of a prime number, except for 0, because 0 GCD of anything is always going to be 0. Yeah? And that's why it's equal to P minus 1, because you're excluding the 0 here. Right? This is for the exclusion of 0. Okay? If P is prime, then phi of P to the power of A will be equal to this. Okay? Or in other words, an easier way to compute this is to just do this. Yeah? You take your prime number raised to the power of A minus the prime number raised to the power of A minus 1. And then in general, if you do the prime factorization of your number n, you can always compute your phi of n as this huge formula here. Typically, we don't really use this last property. Making use of these ones is most of the time good enough for any question that you're going to do. Okay. Note that the last property can be derived by using the first and third property. For a pair of primes, yeah, you can have a look at this yourself if you wanted to have a look at how you might want to go about deriving this. Okay. Euler's theorem. Before introducing Euler's theorem, recall that Fermat's little theorem states that if P is prime and the greatest common divisor of A and P is equal to 1, then we have this result here. Okay. So if P here is prime, then A to the power of P minus 1 is congruent to 1. Notice that since P is prime, phi of P is exactly equal to P minus 1 from our previous property here. Right, this one here. And maybe that will give you a bit of an inkling as to where Euler's theorem comes from. Right, because if you notice that phi of P equals to P minus 1, this A to the power of P minus 1 is exactly equal to saying A of phi of P. Correct? Because phi of P is going to give us P minus 1 anyways. Yep. So A of phi of P equals to 1. It's congruent to 1 mod P. Okay, that's essentially what Fermat's little theorem is for when P is prime. But now we can generalize this into Euler's theorem, which is going to give us exactly what we said basically here. Yeah. A to the power of phi of any number is congruent to 1 mod n. And this number n no longer needs to be, oops, I don't know why I wrote P there. No longer needs to be prime. Okay? And that's essentially Euler's theorem. It's a generalization of Fermat's little theorem. Okay? I'll actually open up a slide here and do an example. So let me get rid of this. Let me edit pages. Okay, set a page. All right, and let's go back out of here. Okay. All right, so let's have a look at an example of using Euler's theorem. Okay, I'm sure most of you guys would have seen this in test 3, I believe. But I also wanted to show you guys a little trick that I personally use when doing these sort of questions. So for example, we have 2 to the power of 512 is congruent to what? Mod 231. Okay. All right, how can we go about doing this? Well, we want to apply Euler's theorem, right? This power here is huge, and by using Euler's theorem, we can probably reduce it to something much simpler. Okay. All right. So first thing to do is, if you want to use Euler's theorem, we need to know what this is. Okay, need to find phi of 231. Okay. This is where my first trick comes in, right? This isn't really just like a calculator trick. But on your calculator, I don't know if you can find it yourself, but just above the button with like speech bubbles, right, the one below square root and above the speech bubbles, in between you will see in yellow, it says the word fact, F-A-C-T, right? So I'll just write down here on your calculator. You should be able to find a button or find a yellow text that says fact. Okay? And essentially what we can do is type in the number 231, press equals, so that it pops up in the answer box, press shift, and then press the speech bubbles, and that will essentially just factorize the number for you. Okay? So straight away in a calculator, you can see that 231 is actually the same as phi of 3 times 7 times 11. Okay? And then you can apply the multiplicative property of phi and get phi 3 times phi 7 times phi of 11 immediately. And then you're done, right? Because phi of 3 is a prime number, because that's exactly what your calculator does. It does prime factorization. So all these numbers here are prime. And so phi of 3 is 2, phi of 7 is 6, phi of 11 is 10, and you ultimately get 120. Okay? And that way you can calculate your phi's very quickly. All right? Next, make use of the 120, right? Because then that means we now know by Euler's theorem that this is congruent to 1 mod 231. Okay? So this is by Euler's theorem. Okay? And so we can find multiples of 120 in 512. So we get 2 to the power 512 is the same as 2 to the power of 480. That's 120 times 4 times by 2 to the power of 32. Right? And that is the same as, whoa, I don't know why I wrote so many little dashes. Let me fix that. That would just be the same as 2 to the power of 32 mod 231. Okay? Alright, from here, sometimes you may be lucky enough and this power is already small enough for you to just plug in a calculator and just brute force it. Right? For example, if it's 2 to the power of 10, you can just put in a calculator, 2 to the power of 10 divided by 231, find the greatest integer, and then just find out, and then just easily find out your remainder from there. If you can't quite get something that fits in a calculator just yet, what I recommend doing is this, like my next trick, I guess, is firstly store your answer on your calculator as, let's say, 2. Okay? Then in your calculator, type 2 to the power of answer divided by whatever your mod is. And say it's 231. Okay? And as you change your stored answer from maybe 2 to 3 to 4 to 5 to 6, blah, blah, and so on, you will get different numbers here, right? It will be a decimal number most of the time. And you want to keep doing this until you find, so for example, you have some whole number value and then dot and then your decimal values, right? These are your decimal values. You kind of want to keep going a little bit until you get decimal values that are sufficiently small, right? Because sufficiently small decimal values mean that you will have a sufficiently small remainder, right? Remainders and decimal points are pretty much like one-to-one correlated. So the smaller your decimal values, right? For example, if you get 0.002, that's really good, right? Because that would mean that you have a very small remainder. Yeah. So in this case, I'll do exactly that. I'll store 2 as my answer. I go 2 to the power of answer divided by 231. That currently is a number even smaller than 1, so that won't work, right? Because we need to have at least one multiple of 231 in this thing that we're dividing by, or like dividing through to, right? So I keep increasing it. Store answer is 3. Does that work? No. I keep going until I hit 8, okay? And I get that 2 to the power of 8. Give myself some more space here. I get that 2 to the power of 8 divided by 231 is 1.1, okay? 0.1 is good enough, right? Like that's pretty good, yeah? And so I'll go ahead and figure out what my modulo is when I do 2 to the power of 8. 2 to the power of 8 divided by 231 is 1.1, so I'll just do 1 times, and I end up getting 25, okay? So it turns out that 2 to the power of 32 is congruent to 2 to the power of 8 to the power of 4, right? Which is congruent to 25 to the power of 4, right? So 2 to the power of 8 modulo 231 is 25. 25 to the power of 4, and now we should have a small enough number. 25 to the power of 4 isn't that big. So 25 to the power of 4 mod 231. You can just calculate it by brute force now on the calculator. And that should be congruent to, I'll just work it out real quick. 1691 times 231, and that's equal to 4. Okay. Essentially, the whole process is firstly apply Euler's theorem. If you have something small enough to brute force in your calculator, you're done. If you don't have something small enough to brute force in your calculator yet, you have to keep reducing it until you do have something that you can. And to do this brute forcing, there's a more systematic way, which I like, which is just to trial and error answers progressively until you get a small enough decimal point, and then use that particular power of your number. Okay. All right. You don't have to do it this way, but it's just a little trick that I personally use that makes it a bit faster, in my opinion. Okay. All right. Moving on. So the next thing to have a look at is primitive elements. Okay. So let A be a unit. We denote the order of A to be the smallest power integer, k, such that a to the power of k is, this may be a little bit of a typo, is congruent to 1, modulo whatever we're looking at. Okay. So we define the order of A under modulo m as being the smallest power of k, so the min, so the minimum power of k, such that a to the power of k will be congruent to 1. Okay. All right. And we say that A is a primitive element of UM if the order of A under modulo M is exactly equal to the size of your set UM. Okay? Or in other words, exactly equal to phi of M. Right? In other words, this particular element A can generate all of the other elements in UM. Yeah? So that means it takes, I guess, phi m number of steps before A cycles through every single value in U of M. Yeah, we'll see an example here soon, I believe. So there'll be an example here soon. Okay. Yeah, so I'll just move on for now. We also have that the order of A divides phi of M for any A in UM. That is the order of any element in UM divides the size of UM. If A is a primitive element of UM, then A to the power of k is also a primitive element when the greatest common divisor between k and phi of M equals to 1. Or in other words, if you find A being some primitive element, then all powers of A will also be a primitive element as long as that power k and phi of M are co-prime. Okay. And lastly, if UM has a primitive element, then it will have precisely phi of M primitive elements. Okay. Note that UM may not have any primitive elements to begin with, but if it does, then we have this result. Okay. All right. Just some intuition on this last one on why this might work, right? So if you have a set UM, okay, then in here you will have, I guess, how many elements in here you have phi of M number of elements, right? And now amongst all of these elements, you need k to be co-prime to the phi of the number of elements, so then you have phi of M. Okay. A field. All right. Intuitively, a field is an algebraic structure where the notion of addition, subtraction, multiplication, and division makes sense. So kind of our real numbers or our integers, you can add, you can subtract, you can times, you can divide, and it will make sense. Okay. More precisely, a bit of a typo here, but yep, let's fix this later. More precisely, a field F is a set of elements together with two operations, plus and multiplication. Okay. Plus is already good enough to define addition and subtraction. Subtraction would just be the inverse of addition. And times is good enough to do multiplication. And it's nearly good enough to do division, of course, omitting 0. Right? Because dividing by 0 may cause some problems. All right. So we have closure under addition and multiplication. That means if we take two elements from the field F, adding the two elements will also return back another element from the field F, and multiplying the elements together will also return another element within the field F. We have associativity and commutativity, I guess. So these two. So we've done these here already. And the last one is that there will be an existence of an additive and multiplicative identity. Usually the additive identity is denoted by 0, and the multiplicative identity is denoted by 1. Yeah. Okay. Existence of additive and multiplicative inverses. Right. So if you have a field, that means for any element, you will always have an additive inverse. So always an element such that when you add on the inverse of A additively, you'll get back to 0. And similarly, a multiplicative inverse, so that whenever you do A times by its multiplicative inverse, you always return back to 1. Okay, and it's also the distributive laws. Okay, we have a remark here. ZP is a field if and only if P is prime. Okay, I believe they went through this in the lectures, but essentially, the only problem that ZP has, whether it's a field or not, is the something to do with 0. Is the existence of multiplicative inverse being the only condition that may cause an issue instead of P. But in the lectures, they showed that as long as P is prime, then this won't be a problem. So I guess I'll bounce it off like this. This won't be a problem. Okay. And that's just because a prime number is going to be co-prime of every other number. And so you will always be able to find a inverse that is within the set. Okay, that was essentially the main idea there. That made P being prime special, was that P would then be co-prime with every other thing in the set. Okay. Okay, now let's have a look at applying this to polynomials. Let f and g be field and then this square bracket x. That essentially means, for example, I'll do an example here. You have z 3x. That just means you have a polynomial, right? Any sort of polynomial. Let's say a0 plus a1x plus a2x squared plus blah, 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 all the way up to anxn. And this just means that all of your coefficients, a0 to an, so a0 to a1 to a2 to blah, 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 to an, all belong in your field. Okay? That's what that means, right? This is what this denotes. We can define the factor and remainder theorems similarly as we do normally. Okay, so if f is within our fx and c is an element of f, then we can write fx equals to qx times x minus c plus fc. So essentially, we're taking this as the divisor, right, the factor. This is our initial polynomial. I'm going to take our, sorry, get some water. and we take our initial polynomial, perform long division on it with respect to x minus c, our factor, and we get a quotient polynomial as well as a remainder. Okay? And the factor and remainder theorem is basically saying, well, the factor theorem is basically saying, if I am dividing by the factor x minus c, and I plug c into my function, my initial function f, and it returns 0, then it means that x minus c will perfectly divide f of x, right? Or in other words, there's no remainder left over. Okay? Yeah. So again, if we have, well, I guess this writes it here perfectly. So if f of c equals to 0, then we will have that x minus c perfectly divides fx with no remainder left over. Okay. I guess I'll also briefly mention remainder theorem here. And the remainder theorem would be, the remainder theorem is that whenever you take some fx divided by some other polynomial, let's say, I don't know, let's just say a polynomial of order, I can't write in words, polynomial of order, let's say n, okay? So this is fx divided by some polynomial of order n, then its remainder will always be of a lower order, i.e. n minus 1 or lower. Right? So it's just saying, for example, if I have some polynomial, let's say x to the power 7 plus x to the power 5, and I'm divided by the polynomial x squared plus 1, then, okay, at the moment, I don't know what it will end up being, right? I don't really know. But I will know for sure that the remainder must be something that is of a lower degree than 2, right? Because the thing we're dividing by is a quadratic. And so our remainder must be lesser in order than a quadratic. So it would be a linear function at best, at most, right? So I don't know if it ends up being a constant. I don't know if it ends up being 0. I don't know if it ends up being some other linear function, but I know at most it can go up to being a linear function, okay? All right, let me also introduce the idea of irreducibility here, okay? Additionally, we say that a polynomial f is irreducible if there are no proper factors of positive degree. It turns out to be very useful to talk about irreducibility. Okay, so that would mean that under whatever field we're talking about, right? For example, if we go back to let's say we're talking about the reals, right? So under the reals, back in high school, you may have learned, for example, I don't know, once you get up to here, this is irreducible. Okay. Why is this irreducible? Well, that's because I've already factorized this as much as I could under the reals, right? Of course, those of you guys who have learned complex numbers then realize that, well, under complex numbers, this isn't irreducible because I can further reduce x squared plus 1 into x minus I, x plus I, right? So for whatever field we're working over, irreducibility is essentially a situation where you have factorized a polynomial so much that you're at a point where you can no longer factorize it anymore under that particular field. Okay? All right. Now we have a little result here. Let f be a polynomial. The set of polynomials zpx, so that means the polynomials over the field zp, modulo f, so modulo the initial polynomial here f, is denoted as zpx slash, and then this little, I don't know, sharp bracket f, okay? If f is irreducible, then this set here will form a field, okay? Let's see an example of this. That's when I first saw this, I was quite confused as to what this means. All right, just a very short example. Right, let's consider, let's say, Z5 x, and we omit the polynomial, or like divide 3 by the or modulo 3 by the polynomial, let's say x cubed plus 2x plus 1. Okay? So what this will essentially do is it will take every polynomial in existence under Z5 and modulo it 3 by x cubed plus 2x plus 1, right? And in general, what will this result in? This will result in the set, so I'll write it again here. This will result in the set ax squared plus bx plus c, and given or under the condition that a, b, c are all in Z5. Okay. So what does this mean, right? How did I get this in the first place? I got this by the remainder theorem, right? We're dividing 3 by x cubed plus 2x plus 1. This is order 3. And so by the remainder theorem, the remainder can be at most order 2, right? That's why I have a quadratic here, right? A general quadratic here. And then furthermore, the coefficients of this quadratic must lie within the field that we're working with, right? And so that's why our coefficients a, b, and c must be elements of Z5, right? And now if you ask me, for example, how many elements do we expect to see in this set? Well, we will expect to see 5 to the power of 3 elements. Why is that? Well, that's because each one of these a, b's, and c's can choose between the values 0, 1, 2, 3, 4, right? So each of them have 5 different values you can choose from. So it'd be 5 times 5 times 5 would be the combination, would be all the combinations of a, b, and c's that you can choose. Okay. All right. Hopefully that makes sense. All right. Primitive element in a polynomial setting. Okay. Very similar to what we defined earlier. Yeah. Again, you wanted to have an order that's exactly equal to the size of your UM. Okay. So, in other words, a primitive element of a in the polynomial setting is exactly the same thing, right? If you can find some sort of alpha, right, such that as you raise the power of alpha, it will cycle through every single value in the set until you reach the size of that set. Alpha the power of the size of that set will be exactly equal to 1. Okay? I think it's much easier if we look at an example here. So let's have a look at this. Suppose we have this set here, or sorry, this field here, because 2 is a prime number. F2 equals to Z2x modulo M1, where M1 is equal to this. Okay. Now, firstly, by what we looked at just here, how many elements will there be in this field F2? Well, there will be exactly how many? 3, 2, 1, 0 to the power 4, 16. All right, there will be 16. In F2. Why is that? Well, that's because by the remainder theorem, if we're going to be dividing 3 by x to the power 4 plus x plus 1, this is order 4, right? Which means our remainder polynomial will be at most order 3. So you have an x cubed term, an x squared term, an x term, and a constant term, all of which will have coefficients that can either choose between the value of 0 or 1, since we're in Z2. And so it's 2 times 2 times 2 times 2 to the power 4 is 16. Right, so we should expect 16 elements in our field F2. Now, every field must contain the 0, like the 0 element. And so besides the 0 element, we should expect 15 other elements. Okay? And that's exactly what we see here. Right? Okay? We let alpha be a root of this polynomial. Okay? Maybe it's good to actually open up a new page here. I'll do that. back. Okay, so if we let alpha be a root of m, okay, then we will have that alpha to the power 4 plus alpha plus 1 is equal to 0. And in other words, alpha to the power 4 will be congruent to alpha plus 1 mod 2. Right? You may be wondering why the negative sign's gone. Well, that's because under mod 2, negative 1 is congruent to 1. Okay? And then you can get all of these other values. I won't go through all of them, but I'll go through some. For example, alpha will just be alpha, of course. Alpha squared will just be alpha squared. Alpha cubed will just be alpha cubed. Alpha to the power 4, I can simplify down to alpha plus 1. Alpha to the power 5 will be equal to alpha squared plus alpha. Alpha to the power 6 will be alpha cubed plus alpha squared. Alpha to the power 7 equals to alpha to the power 4 plus alpha to the power cubed. But alpha to the power 4 can be rewritten as alpha plus 1. Right? And this will keep going on forever, right? Until you get all the way to alpha to the power 14. This alpha cubed plus 1. Right? Then you go one extra step to alpha power 15, and you get alpha to the power 4 plus alpha, which is alpha plus 1 plus alpha, which is 2 alpha plus 1. But 2 alpha modulo 2 is just 0, right? Because 2 alpha would be a I guess, composite number that contains the factor 2, right? So this will be congruent to 1 mod 2. And that's exactly what we want, right? We want 15 elements such that by the time you get to the last element that we need, alpha 15 in this case, it gives you back 1. So its order is 15, okay? Which is what we need, right? Because besides the 0 element in our field, we need 15 other elements. And this particular value of alpha that we chose covers all other 15 values, okay? All right, I hope that makes sense. Yeah. So essentially, if you want to find a primitive element, what you needed to do is you needed to cover all of the other elements in our field, excluding the 0 element. Okay. All right. I believe there's actually a shortcut to this, and that is using this result here. Yeah. We know that there are we're going to need 15 elements out of alpha. And so the only powers of alpha that actually matter is alpha power 1, alpha power 3, and alpha to the power 5, right? If alpha to the power 1, 3, and 5 do not revert back to 1, right? So if we know this is equal to 1, if it does not revert back to 1 by then, we will know that it will for sure work out, right? But for the intended purposes of this course, most of the time, you'll need to write out the entire thing anyways, okay? Because you'll need it to do calculations like this and like this, okay? So although it's a it's a neat trick to ensure that you're on the right track, right? So if you get to alpha to the power 5 and you still haven't encountered 1 yet, then you know you're for sure on the right track, and if you finish it off, it will for sure be right, yeah? But at the end of the day, for most questions, you'll still have to finish it off entirely to do questions, okay? So let's have a guess simplifying alpha to the power of 8 plus alpha plus 1 over alpha power of 11 plus alpha squared. Okay, it should be on the slides right here. Right, so alpha to the power of 8 is exactly alpha squared plus 1. Alpha plus 1 is alpha plus 1. Alpha power of 11 is alpha cubed plus alpha squared plus alpha. And alpha squared is alpha squared. Since we're in modulo 2, any multiple of 2 will be cancelled out to 0. So 1 plus 1 is 2, that's gone. Okay. Alpha squared plus alpha squared, that's 2 alpha squared, that's gone. And so we're left with alpha squared plus alpha over alpha cubed plus alpha. Alpha to the power of 5 is exactly equal to alpha squared plus alpha. And alpha cubed plus alpha is exactly equal to alpha to the power of 9. Okay. And so we get alpha to the power of negative 4, right? But we can revert from a negative power to a positive power because we know alpha to the power 15, I should add that here, is equal to 1, right? So we will have 1 times alpha, so this is equal to 1 times alpha to the power of negative 4, right? But one is after the power 15, so we get this, and so we get this. Okay. And then I'll open up a new page to do this one down here. So let me just open up a new page. Okay, so in this case, I want to solve this. This is 7236, 7236, right? Times by something equals 2. I think alpha and 1. Alpha and 1. Okay. All right. After we solve this, let's firstly make the augmented matrix. So that'll be the same as solving, or I guess row reducing and then backsubbing this augmented matrix here. Okay. Let's say firstly we can do this. The way that I thought about doing this was to just take alpha power 6 minus alpha power 4 times alpha squared, so you get to 0. Right, so what I did here was I did row 2, you plug in row 2 minus alpha 4 times row 1. Okay. Yeah. So I just take the second row and minus alpha power 4 times the first row. Right. So in this case, I'll get alpha cubed minus alpha 4 times alpha power 7. Right. So that would be alpha to the power of 3 minus alpha to the power of 11. Right. 7 plus 4 is 11. And also 1 minus alpha to the power of 5. Okay. Well, what's next? Well, then that means I know from the second row here that alpha cubed minus alpha to the power of 11 times x equals to 1 minus alpha to the power of 5. So x equals to 1 minus alpha to the power of 5 over alpha cubed minus alpha to the power of 11. And then this will just become the same exercise as what we did here, right? Where you just find the values and match them up, and then you reduce it to a simplified value. Okay. I'll leave this for you to check, but I personally get that x equals to alpha power 5 in the end. And then by back sub to find y, I get that y equals to alpha to the power of 11. Okay. So this you check yourself. Okay. All right. A Galois field, okay, usually denoted by GF and then in brackets the number of elements in it. Okay. Okay, so F is a finite field. Then the magnitude of F, or the cardinality of F, is going to be P to the power of n. We've seen this multiple times already, right? We looked back up here. The number of elements was 16. That's 2 to the power of 4. We just saw one here. 5 to the power of 3. Right? So it's usually equal to the prime value to the power of I guess the order of your polynomial. Right? Okay. All right. And yeah, the Galois field is kind of just like another way of representing the same thing that we saw here. All right. For example, we can just express Z. Actually, look at an example that we saw here. Z. Hello? Sorry about that. I'm not sure what happened to the stream, but yep. Let me keep going from where I picked up. Sorry, from where I left off. Yep. So I wanted to have a look at. Okay, my working out for that disappeared. I was looking at Galois fields. I'll just make a note here. Missing. Okay, I'll write it up a little bit later. Okay, so here we have that we were looking at the example of z2x modding out this polynomial here, right? And like we just said, this had 16 elements within it, and so we could also denote this just as GF16. Right? That's what we're saying. Okay, and we can just denote it as GF16. All right, and this field F has precisely phi of q minus 1 elements. Q minus 1 primitive elements. Okay, so in this case, it's saying phi 15 equals to phi of 5 times phi of 3, which equals to 4 times 2 equals to 8. So there's 8 primitive elements in this field here. Okay. All right, the last part of chapter 5 is primality testing. Right, so all this stuff was, I guess this stuff is a little bit more important, right? It will pop up a little bit again in chapter 6 and 7, polynomials. This last bit is completely irrelevant to what we just did. It will do nothing related to polynomials and modular and whatnot. This is simply just testing, like different tests as to whether a number is prime or not. Okay, and in our course, we mainly cover these three. This you can have a look into yourself, but it won't really be covered in the lectures or in the tests. But these three may maybe. Okay, so the pseudo prime tests essentially all just like algorithms. Okay, so there's no, you don't really need to know the theory behind stuff. Just if you know how to use the algorithm, it's good enough. So you put in some integer n, and if n is composite, then return no. Obviously, if n is composite, then it's not going to be a prime number. However, it might not necessarily return no. All right, so the algorithm is you first check if your some arbitrary base that you choose a is coprime of n. Okay. If it's not, then n must be coprime, right? If it's not, then n must be composite, right? That means n and some base has a common factor, which means n isn't prime. Okay. Otherwise, if that's not the case, then you can have a look at a to the power of n minus 1 and see if that is congruent to 1 mod n, right? If it is, then n must be composite, okay, by Fermat's little theorem, all right? Is that correct? I thought it should be, then n must be prime. Let me have a look. A power of n minus 1, what does this one say? I believe there may be a slight error here. Let me have a look. Yep. So this is slight error. It should be, if this is not congruent to 1, then it's composite. On the other hand, if a to the power of n minus 1 is congruent to 1 mod n, then n is possibly prime. Yeah, I believe that is. Yeah, then n is possibly prime. Okay, and we call it a pseudo prime. Okay, the reason why it's not fully prime yet is because we've only really tested this out for base a, right? If you change the base, then it might not hold anymore, right? So it's only a pseudo prime base a, right? In order for it to be completely prime, it will have to be pseudo prime base every number in the natural numbers, which we can never fully check. Okay. Next, we have the Lucas test, which basically is, again, similar thing, just an algorithm. Right, so first you check, does n have a common factor with some arbitrary base a, some arbitrary number a? If it does, then it's clearly composite, right? If there is a common factor with a other number, right? Next, if a to the power of n minus 1 mod n is not congruent to 1, then n must be composite. Same thing as pseudo prime test so far. Then they add one extra layer of complexity, and that is if a to the power of n minus 1 divided by p it's not congruent to 1 mod 1. So what is this? Mod n? Sorry. Mod n. Then for all primes that divide n minus 1, okay, so if this is satisfied for all prime that divide n minus 1, then n is a prime. Okay. All right. This one we don't really have that much of as well. The next one is the other main one, so pseudo prime and Miller-Robin test, right? We have an input again, integer n. If n is composite, it will return no. Otherwise, if it passes through all the tests, it will be possibly prime, similar to the pseudo prime test, except this is stronger. Okay. So first, we write the integer n in this form here. You find as many multiples of 2 as possible in n minus 1, and then times it by t. Okay. Then you choose some arbitrary base again. All right. Then, if a to the power of t is congruent to 1 mod n, then it's possibly prime. Okay. And if this condition fails, you can check the next condition, which is for r going from 0 all the way to s minus 1. If for any value of r this is true, then n is also possibly prime. All right. And in particular, if either are satisfied, then it is called a strong pseudo-prime. Base A. Okay. Similar concept to pseudo-primes. It's done by these different A's, like different bases. And in this case, if it passes either one of these conditions, then it will be a strong pseudo-prime of that base. Okay. Let's just go through one more quick example, then I'll pass it on to Jerry to do the last 2 chapters. Show you that this number, 645, is a pseudo-prime base 2. You may assume that 2 to the power of 28 is congruent to 1 under modulo 645. Okay. So how might we go about doing this? Well, what we need to do is check if 2 to the power of 644 is congruent to 1 mod 645. All right, we need to check this. Okay. And if that is the case, then we can say that 645 is pseudo-prime base 2. All right. So we notice that 644 is the same as 28 times 23, right? And we do know that 2 to the power of 28, by the given hint, is congruent to 1 mod 645. And so that's exactly equal to 1 to the power of 23, which is obviously congruent to 1. Okay? 1 to the power of 23 is still 1, right? And so ultimately, we do get that 2 to the power of 644 is congruent to 1 mod 645. And therefore, the number 645 is a pseudo-prime base 2. Okay? All right. And that pretty much wraps up what I have to talk about for chapter 2. I will now pass it on to Jerry, who will cover chapter 6 and 7. Right, chapter 6 shouldn't be too long, and then, yeah, some more stuff about chapter 7 on deciphering. Okay? All right. Thank you, everyone, for, I guess, sticking around. I'll now pass it on to Jerry to do his part. Okay.
Testing sound. Testing sound. Okay, cool. Hi, I'm Jerry, and I'm going to be doing chapter 6 and 7, so algebraic coding and cryptography. So we start with chapter 6, algebraic coding. And first, we're going to revisit Hamming codes that we looked at in chapter 2. So for a Hamming 7-4 code, consider a parity check matrix that looks like this. And recall that the Galois field, order A, can look like this. And let alpha be a primitive root of x cubed plus x plus 1. And what we can kind of notice is that the columns of this check matrix correspond to coordinate vectors of the powers of 1 alpha all the way up to alpha to the power 7. So for example, alpha to the power of 5, which is this column, this is represented by a coordinate vector 1, 1, 1. Sorry. 1, 1, 1. And that's because alpha to the power 5 is equal to 1 plus alpha squared. One, one, one. And therefore, we can represent the columns of H by the powers of the root alpha. So here we have 1 alpha and alpha to the power 7. And now we consider a code word, C0, C1 up to C7. And the syndrome of the code word is when you do matrix multiplication of the check matrix with the code word, and then we get C of x, which is a polynomial corresponding to C, where we can see that the coefficients of this polynomial Cx, these are equal to the numbers in the code word. And so this notation Cx, this allows us to describe a code in terms of polynomials. So if we look at a polynomial fx of degree m with primitive root alpha, and we let m be 2 to the power of m minus 1, and k is n minus m, we have like the matrix that we just looked at, and it goes, the powers of the matrix go from 1 to alpha to the power of n minus 1, which we found here. And this represents the check matrix for a binary Hamming code. And every binary Hamming code can be obtained this way. Now, if we have a code word, C0 to Cn minus 1, we have that the first m bits are the check bits. And the next k bits are the information bits. And since we have the first m bits of the code word being check bits, that's because the first m columns of H are the leading columns. So if we look at this check matrix that we've looked at earlier, what we can notice is that these first 3 columns are leading columns. And if we recall from chapter 2, the check bits correspond to the columns of the check matrix that are leading. So the neat part of BCH codes is that the first m bits are going to be all check bits, and obviously the rest are going to be information bits. So the information bits and the check bits are neatly divided. And for single error correcting BCH codes, the syndrome of a code word is when you do matrix multiplication with the check matrix with the code word transposed, where Cx is the code word polynomial corresponding to C, where the coefficients of this polynomial correspond to the code word. And just like with binary Hamming codes, the syndrome of the correct code word is going to be 0. So C of alpha is going to be equal to 0. So this means that alpha is a root of the code word polynomial Cx. Now what this means is that since alpha is a root of Cx and alpha is primitive, the minimal polynomial m1 of x of alpha divides Cx, and m1x is a primitive polynomial fx, because alpha is going to be a root of m1x, so that means m1x is primitive. Now we go through the more important part of BCH codes, which is encoding, decoding, error correcting for single error correcting BCH codes. So first we look at encoding. So we're going to start with a message, and if we remember, our message is k equals n minus m bits in length. And from these k digits, we form an information polynomial. So where all the coefficients of this information polynomial corresponds to the bits in our message. So we'll see that for x to the power of m, the coefficient is cm, and for x to the power of n minus 1, the coefficient is cn minus 1. So we form an information polynomial using the bits we get from our message. And then afterwards, we calculate something called the check polynomial. And the way the check polynomial is calculated is, first of all, you start with the information polynomial, and then you apply modulus m1x, which was the minimal polynomial of root alpha. And the way that we calculate this when we do it manually is through polynomial long division. And we'll get to see an example of how polynomial long division works out to find the check polynomial later. So afterwards, we have found Ix and Rx. And to find the code word polynomial, what we do is just add them together. So Ix plus Rx. And then we look at the coefficients of this code word polynomial, which is going to be C0 to Cn minus 1. And that's our code word that has been encoded from our message. And now the first m bits of this code word are going to be the check bits, and the last k bits are the information bits, which correspond to the message that we wanted to encode. Now we look at error correcting and decoding. So when we receive a BCH code, we ideally want to receive C, which is just a code without any errors. But we might receive a code D, which is C plus EJ. And EJ represents when there's an error in the alpha to the power of j position. So for single errors, if we have a code and so on, if there is a single error in this code, it might be in this position. So instead of a 1, we have a 0. So that's going to be represented by the code word plus 1 in this position. And now let us represent C and D as code word polynomials Cx and Dx. So this means that the bits of C and D, they correspond to the coefficients of these polynomials. And then we calculate the syndrome of D. So that is equal to D of alpha, which is equal to C of alpha. And then since there's just plus 1 in one position, we also get plus alpha to the power of j. And C of alpha simplifies to 0. So what we're left is alpha to the power of j. So once we calculate the syndrome and we realize that the syndrome is not equal to 0, that means something's off. And in this case, this means that there's one error. So after we've calculated the syndrome alpha to the power of j, what this tells us is that in the code word D that we've received, the j plus 1 letter of the code, or the j+1 bit of the code is wrong. So we just have to change it from 1 to 0 or 0 to 1. And decoding a BCH code is very, very simple. So once you have the code word C, you just look at the last k bits, which are the information bits. So we don't do any examples for the single error correcting case. So we just move straight on to the 2 error correcting case, because solving the 2 error correcting BCH case is pretty much similar to the single error correcting case. And for the most part, the exams kind of tend to examine the 2 error correcting case. So yeah, I'll just move on to the 2 error correcting case. So if we look at the single error correcting case, we used one root, which was alpha, of a minimal polynomial m1x. So we record this theorem from chapter 5, which is that if p is prime and beta is a root of fx, then so is b to the power of p to the power of I, or for all I. So for any finite field with primitive element alpha, if alpha to the power of s is the root of the polynomial, then so is every element of the set. So most of the time, we look at z2 x, so p is 2. So if we usually have alpha as one of the roots, then alpha squared, alpha to the power of 4, and so on are going to be also going to be roots of our minimal polynomial m1x. And so we're interested in these indices of these powers of alpha. And this is called the cyclotomic coset containing S. So if we start with S and we multiply S by P, and then we just keep going. And at some point, it could be P to the power of 4S, but once you apply the modulus, it might simplify into one of the other elements in this set. So yeah, this set is definitely finite. So for the single error correcting case, the roots of m1x are alpha to the power of j, where j is the coset for 1. And in order to have 2 error correcting capabilities, we need a different root not in m1. So the reason why we need 2 roots not in the same polynomial for the 2 error correcting case relates to the syndrome that we're going to look at soon. And pretty much, if we looked at the syndrome for the single error correcting case, we end up with just like a scalar value, or like just a one-dimensional value. So what we're going to end up looking at later is we look at a syndrome that is 2 dimensions. So those 2 values helps us differentiate between cases between 0, 1, and 2 errors. And so we consider a field. We have that p equals 2, as shown by here. And so we find 2 cosets, one of which is not k1. So obviously, just like the single error case, we're going to look at alpha and the minimal polynomial for alpha. And we find that the coset for 1 is 1, 2, 4, and 8. And we realize that 3 is the smallest number not in k1. So we look at the coset for 3, which ends up being 3, 6, 12, and 9. So that means the root for the minimal polynomial m3x, that's going to be equal to x minus alpha cubed, since these are the indices of the power of alpha. So yeah, m3x, the minimal polynomial for alpha cubed, simplifies into this polynomial. So pretty much, if you wanted to show this, we have our table of what each power of alpha is equal to. So alpha to the power 5 might equal to like 1 plus alpha or something. So once this equation is fully expanded, or this polynomial is fully expanded, the alphas all disappear and turn into like 1s and so on. And so now we have two minimal polynomials, m1x and m3x. And so we're going to define a polynomial called mx, which is the product of these two minimal polynomials. And this means that alpha and alpha cubed are roots of this big polynomial, since this polynomial has root alpha and this polynomial has root alpha cubed. So we're going to look over at how two-error BCH codes are constructed, but it's not as important as encoding and decoding. So kind of like what we did in this previous example, we're going to want to find another minimal polynomial, and we're going to define a big polynomial that's the product of these two minimal polynomials. So right now I'm more interested in this new check matrix. So we can see that there are two rows in this check matrix H, and the columns of this check matrix. So this is like the single error case where we have powers of alpha, because that was the root in the single error case. But now alpha to the power of I is also another root. So we have powers of alpha to the power of I. And now since our check matrix H is two-dimensional, well, it has two rows, the syndrome of the code word is also going to have two rows. So we're going to end up with the code word polynomial evaluated at alpha and evaluated at alpha to the power of I. So for encoding, so it's pretty much the same as the single error case, except that the way we find the check matrix, so we still have the same information matrix, not the check matrix, check polynomial. So yeah, we start off with the same information polynomial, but now we use modulus big mx. So before we use just the minimal polynomial for alpha, but now we use mx, which is the product of the minimal polynomials for alpha and alpha cubed. So yeah, so we're just going to end up dividing ix by this bigger polynomial mx to find the check polynomial rx. And decoding is just the same as before. So once we end up receiving the code word and like encoding it and sending it over, we just have to look at the last k bits of the code word. Now, especially given by its name, two error correcting BCH codes, we can correct up to 2 errors. So now, again, say we receive a code word D, where C is the actual code word, and we have plus EJ and EL. So this represents that the code word C has errors corresponding to the positions alpha to the power of J and alpha to the power of L. And just like before, we represent C and D as code word polynomials, where the coefficients of these polynomials correspond to the bits in C and D. And once we calculate the syndrome, we'll see that the parts corresponding to the actual code word C are going to separate out into here and turn into 0. But what we're left is, due to these errors, EJ and EL, we're going to be left with these extra bits, alpha to the power of J and alpha to the power of L. And similar to the bottom entry here. So obviously, there's going to be 0 errors when the upper and bottom entry of the syndrome is 0. So that's just been consistently the case. But if the syndrome is 0, then there's no problem. Now, if we see that the upper entry of the syndrome, d of alpha, which is the polynomial dx evaluated at alpha, if that's not 0, then there's either 1 or 2 errors. And the way we differentiate between the case where there's one error and the case where there's two errors is to just apply this calculation. So we're going to end up with these two terms. And we see that if we raise d of alpha to the power of 3, if that's equal to d of alpha cubed, then there's just going to be one error. And if they're not equal, then we have two errors. And then we like look for the errors accordingly. So let m1x be x to the power 4 plus x plus 1, and let alpha be a root of this polynomial. We may assume that f is a field with the following description of its non-zero elements. So just because we just did chapter 5, this should be really fresh. And so firstly, we have to express alpha to the power of 10 and alpha to the power of 11 as linear combinations of the powers 1 to alpha cubed. So we know the value of alpha to the power of 9. So to find alpha to the power of 10, all we do is apply alpha to the value we know, which is alpha to the power of 9. And this simplifies into alpha squared plus alpha plus 1. And then similarly, once we've found alpha to the power of 10, we just apply alpha again to find alpha to the power of 11. So yeah, so now there's no more question marks here. We've fully filled out all the powers of alpha. So part B is to solve the following set of linear equations in F. So yeah, I was having a look at how Jay did it, and yeah, I'm sure that seemed like a good approach, but I just did it more kind of like manually, kind of like expanding the equations out into separate equations, and then applying like simultaneous equations, just a more old school way. So we have a product of these two matrices. So if we just multiply the entries out, we get two equations. So alpha squared times x plus alpha to the power 4 times y. And that's going to equal to the upper entry, alpha to the power 4. And similarly, we get this second equation. And then since there's alpha cubed on both sides, we can divide alpha cubed away. And we end up with a term of x, which is in terms of y. And then if we substitute this value of x into this original equation 1, once we just do a bit more algebra, we end up with alpha to the power 4 plus alpha to the power 7. And then obviously we divide it by the term that's multiplying y. And to simplify this term, we look back at the table that we had, which details like what all the powers are equal to. So for example, alpha to the power 4 is equal to alpha plus 1. So we just add this all up, and we end up with y being alpha to the power of 8. And then once we find y, we sub it for x, and we end up getting alpha to the power 4. So we've solved the values of what x and y are equal to. Okay, so now we look at the third part of this question. So a BCH code has been obtained by replacing a message by the coefficients of a polynomial Cx. And here they just give us a bunch of information. So here we can see that they gave us the polynomial mx, which is the product of these polynomials for the separate roots. And this is the information polynomial Cix, where these are the coefficients corresponding to the message. And Crx, which is Cix, which is the information polynomial, mod mx. And obviously the code with polynomials when you add these two up, the information and the check polynomial. And it says using this code given, encode message m equals to 1110001. So we know that the message corresponds to the information polynomial. So like I've said several times, the coefficients of the information polynomial correspond to the bits in the message. So we have a 1 here. So the coefficient of x to the power of 8 is going to be 1. And since we have zeros here, the coefficients of x to the power of 11, 12, and so on are like equal to 0. So we end up with an information polynomial that looks like this, which corresponds to our message. And now we want to find the checked polynomial, which is equal to the information polynomial mod mx, where this is mx. I'll just point it out. So yeah, on this page, I've just demonstrated how I do polynomial long division. So this is the information polynomial that we are finding the modulus of. So we have the entries where it's non-zero, so x to the power 14, and then the rest is filled with zeros. So yeah, so just for the first term, I'll just go through the first term. So we see that our mx starts with x to the power of 8. And our biggest term that we have to divide at the moment is x to the power 14. So pretty much that's why we have to multiply this polynomial by x to the power of 6 to start with. And once we do, we multiply mx by x to the power of 6 to get this polynomial. And once we do subtraction, we end up with this remainder. And just notice that pluses and minus when p is 2 is somewhat arbitrary. So like x minus y is the same as like x plus y when we only look at zeros and ones. So this is like technically minus x to the power of 13 here, but it just turns into the x power of 13. And for the interest of time, yeah, I'll just be leaving it here and you can look at the working. But the important part is we finally find what Rx is equal to, which is this highlighted section here. So that's the remainder. And that's therefore the check polynomial, Rx. So now we have Ix and Rx. So the rest is pretty easy. So I just restate what Rx and Ix is equal to. And the code word is just the sum of these two polynomials. And the code word itself, not the code word polynomial, the code word itself just corresponds to the coefficients of this code word polynomial. So I've just aligned it in this way, in a way that's easy to see. So this corresponds to 1 and x, but then since there's no 1 and x, we write 0 for those so that their coefficients are 0. So yeah, so I think our original question was to encode this message, and we have successfully done so. So if we remember, this is what our message looks like. And here we can see that the last k bits of our code word is pretty much the message. So yeah, everything is looking good. And now we have to use the code to correct and decode a message. So we're given a message y, assuming that at most 2 errors occur in transmission. So once you're given a code to decode, you're going to first look at its syndrome. And if it's 0, then it's great. It's like we got the correct code word. But if we look at the syndrome and see that it's not 0, then we do have a problem, and then we have to figure out how many errors we have and where the error is, so we can fix up the code before we decode it and look at what the message is. So we have this code y, which is 1, 1, so there's 5 ones, and the remaining is all zeros. So that's pretty convenient to look at, to be honest. But yeah, so polynomial for this, wait, okay. This should be yx, because that's the code word polynomial for y. But just for the sake of just the notation we're used to, I'll just call it dx for some reason. And dx, so for dx, we have just 1 to x to the power 4, since the rest of the code is 0. So the coefficients for the rest of the powers from x to the power 5 and so on are all 0. So this is the code word polynomial that we get from our message. And so when we find the syndrome of the message, we're going to find that first we're going to look at the syndrome of the check word, the code polynomial evaluated at alpha, and then we're going to evaluate the polynomial at alpha cubed, since that was the other root we looked at. And then so pretty much we're just subbing first, we sub alpha into this equation, and then we sub alpha cubed again to get these two entries. And with these two entries, we're just going to look at the table of the values of the powers of alpha, and this simplifies into these two entries. So d of alpha is equal to alpha to the power of 6, and d of alpha cubed is equal to 0. So straight away, we see that the syndrome is not fully 0. So that means there is at least one error, and at most 2 errors. So I've written here that the syndrome, that's the vector we get. And since this top entry d of alpha is not 0, there's at least one error. And then the way to check and distinguish between the cases where there's 1 error or 2 error is to look at d of alpha to the power of 3 or d of alpha cubed. And so we calculate these two values, and we realize that these two values are not equal. So this tells us that there are 2 errors in this case. So now that we know that there are 2 errors, our job is to find where the errors are and fix them before we decode the message. So if we just remember what the syndrome looks like when there's 2 errors, that's what we end up with, since the rest just turns into 0. So there are errors in positions J and L. So here we have these two equations, and at this point, in order to find what J and L are, we just have to just do some trial and error and to see what fits. And so we first start at J is equal to 0 and L is equal to 13. So when we have J is 0, L equals 13, alpha to the power of 3J is obviously alpha to the power of 0, which is 1. And alpha to the power of 3L is alpha to the power of 39. And since I think alpha to the power of 15 is equal to 1, so this is equivalent to alpha to the power of 9. And that is definitely not equal to 1. So we know that this case definitely doesn't work. And then we just move up once, which is J is equal to 1 now. L is therefore equal to 11. Also, I forgot to mention that the way you find L is dependent on the values of J. So if you pretty much just go from J 0, 1, 2, and so on, and L, this is where you get L. So you just sub in what you got for J, and then once you calculate this, you'll know what the value of L here is. So yeah, so we end up subbing j is 1 and L is 11 into this secondary equation here. And we do find that this is true. So since we found that j is equal to 1 and L is equal to 11, this corresponds to the errors in positions 2 and 12. So yeah, so after you found these positions, we just have to remember to add 1 to both to find the actual position on the message. So just make sure not to make that kind of silly mistake. And so we fixed this second position. So it goes from a 1 to a 0, and this goes from a 0 to a 1. So we have corrected the message. And now they want us to decode it, which is simply just to look at the last k bits of the code word. So this is the decoded message M. So that brings us to the end of BCH codes. So for the exam, just make sure you're pretty good at the decoding and encoding and error correction of the two-error correcting case. That would be my recommendation. So we now look at cryptography. So far, a lot of like the codes we've been looking at, a lot of it's like to save space, like compression codes and so on. But in the field of cryptography, now it's kind of like we're concerned that, hey, I want to send a message to someone, but at the same time, I don't want someone else to like be able to like intercept it and then understand what it means. Like I just want that person to receive my message only, like it's private or something. So if we want to accomplish that goal, we start off with a message, and then we encrypt it with an encryption function into an encrypted message, C. And once we encrypt the message, encrypting and decrypting depends on a key, K. So once you have encrypted a message and then sent it, a cryptanalyst, or just like someone who's just trying to intercept it and see what the message is, they can't decrypt it easily because they don't have the key. And I suppose that the person you're sending it to has the key, so they're able to decrypt it. And there's also like other ways where there's like, you don't need to share a common key and stuff, but yeah, we'll just get into that later. But for now, it's just, yeah, the sender and receiver both have a key, which means that even if someone captures the message on its way, they're not going to be able to like decrypt it and understand what the actual message was. So first we look at the simple substitution cipher. So we just look at the letters of the alphabet, A, B, C, D, all the way up to Z. And one way of doing a substitution cipher is to literally substitute each letter with a unique symbol. So A could be exclamation mark, B could be question mark, and so on. Or, which is like what we're going to be looking at more so in this course, is that we apply a permutation pi to the order of the letters A, B to Z. So, yeah. So we have these 26 letters, and then we like just jumble it up in like a random way. So like A corresponds to P, and L corresponds to O, so on. And if we apply a permutation, there are a total of 26 factorial keys. So keys is like the number of ways we can implement this cipher, or like this permutation. And the reason why it's 26 factorial is because the alphabet is 26 letters. So there are 26 ways we can pick a letter to represent A. And then after we pick one, there's only 25 letters left. So for B, there are 25 ways to represent B, and so on. And that's pretty much equal to 26 factorial. And in terms of just notation, when we encrypt for the substitution cipher, so we here have I and pi I. So encryption is just finding the pi I, and decryption is just like the inverse of encryption. So if you have this table and you receive C, decryption is literally like looking at the corresponding plain text equivalent, which is K. Now we look at something called the transposition cipher. So in the transposition cipher, we're going to divide letters into blocks of length R, and we apply a permutation to the letters of every single block. So for example, let the blocks be 4, length 4, so R equals 4 here, and we have a permutation that looks like this. So what this matrix means is that if we have a 4-letter word math, so there's 1, 2, 3, there's 4 positions that each block of letters can go to. So here, the first letter is M, and here under it, we have 2. And what this means is that the first letter M is going to go to the second position, which is right here. And the second letter A is going to go to the 4th position. The third letter T is going to go to the 1st position, and the 4th letter H is going to the 3rd position. So just for this 4-letter code word, we end up being able to apply this permutation. And so if we have a text that just keeps going, so it's more than 4 letters, of course, we just divide up the text into blocks of 4, and then on each block, we apply this permutation. So that's how the transposition cipher works. And what we can do is that we can apply both the substitution and transposition cipher, and that's going to make the code harder to break. So we can first jumble around all the letters of A to Z. So we first jumble it, and then we divide the text into blocks, and then jumble it again. So that just makes it harder for like humans to crack. So polyalphabetic substitution ciphers. So the cipher we're going to be interested in, that's in this category, is the V cipher. And in this cipher, there are different Caesar ciphers applied periodically according to a key, and Caesar ciphers just shift each letter K places forward. So another way of looking at Caesar ciphers is to look at it in terms of like the Caesar cipher for C is a cipher that starts with C, and it's C, D, and so on until Z, and goes to A and B. And what the V cipher does is that this is our key, which is code, and in every block of 4 letters, the first letter is going to apply the Caesar cipher for C, and then the second letter is going to apply the Caesar cipher for O, and then D, and then E, and then it's repeated. So yeah, just intuitively, like this one seems to be a lot more harder to crack than the first 2 that we looked at. But what we're going to look at now is something called the Kaczynski's method, and it's actually used to help kind of crack this V cipher that we just looked at. And the way it does that, it estimates the length of the key. So here, the key is code, so that the length of the key is 4, and it is really, really helpful in being able to solve this V cipher if we know that the code is length 4, because yeah, that's a very vital piece of information. And the way we're going to be able to calculate and estimate this length is through the probability of coincidence. And that's the probability that 2 randomly chosen letters from a message are identical. But when it comes down to it, we're going to be looking at something called the index of coincidence, which simply just estimates this probability of coincidence. So the formulae for Kaczynski's method is that We have a message, M, and the length is n, so the number of characters in the message is n. So the index of coincidence IC, which is what we want to calculate, is equal to this formula. So here we have n just being the length of the text. And here we have the sum of the FI's squared. And FI is the frequency of each letter in the message. So for example, if A comes out in this message like 5 times, then FA will be 5. If there are 5 A's, we can find. And then once we've found this index of coincidence, now we're able to calculate an estimate for the key length for the periodic substitution cipher. And yeah, so here we have our n's. And here we use the IC that we found. So yeah, once we know n and IC, we can find an estimate for R. So we look at an example. So an English language message has been enciphered using the V cipher. The letter frequencies of the ciphertext are as follows, given by odd and even letter positions. So what this means is that just for A appears in even letter positions twice and in odd positions 3 times. So the total number of times that A appears in this text is 2 plus 3, which is 5. So first they want us to calculate the index of coincidence, IC, and once we've done that, we can plug the value of IC to find the keyword length R. And it's given to us that n here is 51. So first we want to find IC, and each value of Fi can be found in a table. So Fa is equal to 5, Fb is equal to 2, Fc is equal to 2. And to find the sum, we're just going to do 5 squared plus 2 squared plus so on. So here we have 2 plus 2 squared. So this is what Fi squared, the sum of Fi squared is equal to. And then yeah, so we just pretty much calculate it here. And we put it into our calculator, and it comes out to be approximately 0.0478. So that's our index of coincidence. So just like for a refresher, this is the formula for the estimate key length, R. And we just simply sub in the values for n and IC here. And so we estimate that the key length is around 2.82. So I guess it's kind of close to 2 or 3. So yeah, so if we had to guess, it would probably be like 2 or 3. So given that R equals to 2, we must find the key and decipher the message. So what it means when R is equal to 2 is that we have key 1 and then key 2 applied. So there's and then key 1 and then key 2. So all the key 1s respond to a particular, the same Caesar cipher shift, and all the 2s represent another but different, but they're all the same Caesar shift. So another way of just thinking about it is that all the even letters in this message correspond to the same Caesar cipher, and all the odd letters of this message correspond to a certain Caesar cipher. So when we come across a question like this, it's not 100% formulaic in trying to solve it. There's a lot of like trial and error, but it's not to say that there aren't tools that can help us. So the biggest one that stands out to me is that we have a letter here, Q. And so this is an English message, and we have a letter by itself, Q. And in terms of one-letter words, personally, I can think of only A and I. So this means that I'm going to test for the case where Q is representing A and Q is representing I, and then see which one seems better. And then once we've like uncovered a lot of information based on just uncovering one of the keys, one of the components of the key, that's just going to help us. But for now, we're just going to be looking at this letter Q and seeing whether Q is representing A or I. So first, we consider the case where A is represented by Q. So A is like the original text, because like there's a lot of A's by itself in English. So yeah, we consider that A is being represented by Q. And so we have this thing called the V table here, which has all the Caesar shifts that are possible. So to use it, because we're saying that A is being represented by Q, so we start with here A, and then we look down this column until we find Q. So we're considering that this is the Caesar cipher that might be being applied to all the odd letters. So we try like seeing what a bunch of these letters decodes to. So for M, so the way we decode it here is that we see here that the second letter is M. So here we look at M and we go down this column until we go to our Caesar cipher. Oh no, whoops. Yeah, so we start with M. So we look at M here and we go up to see what it's representing. And it says W. And we do the same for Z. It's represented by J. And for T, it's represented by D. And then I've just done this for a few more letters. But then when we kind of look at this, right, we have a 4-letter word here. And here we have like a W and a J. And here we have like a G and a W. So while this may be the correct shift applied, like since we're looking at the cases for A and I think for now we're just going to leave A by itself and then move on to see the case for I and to see if it looks any better. So in this case, we're checking for the case where Q is representing I. And to find that particular Caesar shift is here we have I, and we go down until we see Q, since Q is representing I. So this is the Caesar shift we're going to be looking at. And so we look at M, so the second letter M, and it corresponds to an E. And for Z, it corresponds to an R. And we do the same for the whole thing. And just comparing the previous one, where we said that Q is representing A, here we have like WJs and like Gs and Ws. But then here, we see a lot more of the common kind of, and like in better places, like we see a lot of E's, T's, H's, and so on. So we feel a lot better about the case where Q is representing I. So for now, I'm just going to assume that this is the case. And we're fairly confident at this point that Q is being represented by I. And so what comes next is that this is the key, this is the Caesar shift for all the even letters. So now we have to look at what the shift is for all the odd letters. But now we've solved like about half the message. So we can kind of like deduce from what we already have. So that's something that just like came out to me was that among these odd letters, H comes out like quite often. So we have a H here, H here, H here, and so on. So H most likely represents like a vowel or like a really common letter. And so yeah, H is quite common. And so I just looked at this 4-letter word, and we have something X, something M. And if you just make an educated guess about which letter might be in between X and M, I think A would be a decent guess. So if we're guessing that here, and A belongs here between X and M, we look at the Caesar shift for where A is represented by H, and then for that shift, we're going to be able to like find the decryptions of all the other letters, and if it makes sense, then we can feel good about the message and the way we've deciphered it. And it turns out that if we use this key where A is represented by H, so here we have A, and we go down, it's being represented by H, so this is our other key for the odd numbered letters. And so these red letters represent all the decipherments of the letters according to this Caesar shift. And yeah, we do get a message that makes sense. Dear all, I hope that you crushed the exam and enjoyed the course. So we've deciphered the message, and in terms of finding the key, so the key is the corresponding shifts that we used. So we used the H for the odd letters and I for the even letters. So our key is HI, which is high. So in the ciphers that we just looked at, both the sender of the message and the receiver of the message, they already know what the key is. So for example, we had here that the key is high. So the way that this would work is that the sender is going to encrypt the message using this key high, but they're assuming that the receiver also knows that the key is high. So that obviously the receiver is going to be able to decrypt it, and assuming that just if anyone just randomly just took it and looked at it, they don't know the key. So it's like it's much harder for them. But the problem with this is that at some point the key has to be exchanged, and that can be unsafe, and someone might be able to intercept the key during that exchange. So we look at something which is a new form of cryptography known as asymmetric cryptography, and there is no longer a common key. So like in the case I just talked about, like there wouldn't, in this asymmetric cryptography, like both the receiver and the sender don't have this common key like high. And so they don't have to exchange keys. So there's going to be a public key and a private key. So the public key corresponds to encryption, and the private key corresponds to decryption. And pretty much, it's easy to encrypt and easy to decrypt with the private key, but it's hard to decrypt without the private key. So we look at one of these approaches, RSA approach, which is an example of public key cryptography. And yeah, in terms of like the calculation component of the RSA, this is mainly going to be, it's going to be really chapter 5 intensive. So if, in terms of like the calculations, I'll just kind of like be very brief for it. But in the RSA scheme, each user does the following. So they pick 2 primes, find the product of the primes, and then calculate phi of n. And if we remember from chapter 5, that's really easy to calculate if you have a product of primes. And then we choose a value of e between 1 and phi of n, where the GCD of e and phi of n is 1. And then we calculate d, which is e inverse mod phi n. And to calculate d, we're going to have to do the Euclidean algorithm. So that's like chapter 5 again. So the product of the primes, PQ, it's okay if like everyone knows that. But in the private key, what is special is D. So that's not going to be easy to get for the cryptanalyst. So to encrypt a message, we raise the message to the power of E mod n, and to decrypt the message, or to decrypt the encrypted message, C, we raise it to the power of D. And when we decrypt the encrypted message, knowing the private key K bar, we end up getting M, which is the message, because of these properties that, we covered in chapter 5. So we look at an example. So consider the following encryption scheme. Triples of letters, so like blocks of 3 letters, are encoded as numbers by mapping these letters to A1, A2, A3, where A1, A2, and A3 is represented by a number, which is equal to this expression. The number is then encrypted using RSA encryption with a value for N and E. Decipher the received ciphertext C. So we receive the encrypted message, which is 4729. And if we remember, to decrypt it, we're going to raise it to the power of D mod n. So first, we have to be able to factorize this big number into 2 primes. And since that's chapter 5 stuff, I'll just give you the result. So we can factorize n into these 2 primes. And then we calculate phi of n, which is straightforward. And we calculate d, which is E inverse. So we were given the value of E. And now we know phi of n. We calculate this using the Euclidean algorithm. So we end up with d is equal to 7. And now we're going to raise the code to the power of d mod n. And through calculation, we find that the message is 11,683. So the RSA component of this question has been pretty much done. So the message that they wanted to send was 11,683. And the rest is just algebra. So we have an expression that's like 23 squared times A1 plus 23 times A2 plus A3. And yeah, so pretty much just you first find it's 22 because you divide 11,683 by the biggest block here, which is 23 squared. And the biggest multiple of 23 squared we can fit is 22. And then obviously there's remainder left, and we divide it by 23, and we can only fit 123, and then A3 is just the remainder after that. So the letters that we wanted to send correspond to letters 21, 1, 22, 1, and 22, and that corresponds to YAY or OEA. So the final topic I'm going to look at briefly is called the unicity distance. So the unicity distance represents the minimum amount of the ciphertext required for a unique and meaningful decipherment when trying all possible keys. So it's kind of like you want to be able to decipher an encrypted text. And obviously, like if you have like hundreds and hundreds of symbols, that's going to be like easier. And if you only have like 5 symbols to work off, that's like impossible. So unicity distance kind of represents like the minimum, like the theoretical minimum amount of the ciphertext you need. And it's given by this formula, where K is the total number of keys, Q is the number of letters in the source alphabet, and R is the rate of language in bits per character. But we don't have to worry too long about this formula because this is the formula that we look at most of the time, because for the most part, we're going to be looking at English text, which means that the values of Q and R are established. And we simplify the formula down into just this expression here. So if the keys are equally likely, the expression here is simplified into this expression, log 2k over 3.2, so, and the ceiling of that. So pretty much, if we want to find the unicity distance of an English text where all the keys are equally likely, all we need to know is the total number of keys, which is this k over here. So we have a question. A product cipher on an English text is formed by applying a simple substitution cipher and then a transposition cipher of length 9. So they want us to find the number of possible keys and to find the unicity distance for the cipher. We did talk about a combination of substitution and transposition ciphers earlier. So pretty much you just multiply the number of keys you can do for both if you want to just combine it. So there are 26 factorial ways to apply a substitution cipher, and there are 9 factorial ways to apply a transposition of length 9. And therefore, the total number of keys when you're doing both is to simply just multiply them together. So we get the number of keys, total number of keys being 26 factorial times 9 factorial. And because it's an English text and we can assume that all the keys are equally likely, we can use this formula for unicity distance, where all we need to know is the total number of keys k. So we sub this value into here, and we end up finding that the unicity distance is 33.4. So the final part is that we get a message of length 50 that's enciphered using this product cipher, and this resulting cipher text is intercepted by Eve. Imagine that Eve is trying all the possible keys. Would Eve just expect to decipher the text in a unique and meaningful way? So just going back to the definition of unicity distance, there's a lot of terms that we heard. So we heard given you try all the possible keys, and also the minimum, not the minimum, just is she able to decipher the text in a unique and meaningful way? And that's determined by the unicity distance, which we calculated to be approximately 33.4. And since Eve is given a text message that has length 50, theoretically she should be able to decipher her text in a unique and meaningful way. So that comes to the end of chapter 7, and that's it for the course. So thank you for listening, and good luck for the exam. Thank you.